So make sure you have your guided notes that'll help with the note-taking process. If you need to pause at any time, please do so. And just tell the sub to pause it. All right, so we're going to talk about exponential functions, and we'll do differentiation and integration. But I want to remind you about some things about exponential functions. Remember that logarithmic functions and exponential functions are inverses of one another. So if I have f of x is a logarithmic function, then f, the inverse, remember that's f with a little -1 on it, is the natural exponential function. Okay, and there's our notation to show that. And also a reminder about inverse functions, that they are symmetrical over the line y equals x. So their graphs look symmetrical, they're reflections of one another. Remember some properties that if I do a composition of either one, so if I do the natural log of e to the x, that's just x, and vice versa, if I do e to the natural log of x, then that is also equal to x. We have the product rule of exponents, so that if I have e to the a times e to the b, then that's e to the a plus b. We have our quotient rule, that's where we subtract the exponents. Keep in mind that our domain of e to the x is all real numbers, and that their range is positive real numbers, right? Remember, those are switched from the natural log. E to the x is always continuous, increasing, and one-to-one on its entire domain. And the graph of e to the x is concave up on its entire domain. All right, keep in mind that the limit as x approaches negative infinity of e to the x is 0 because of that horizontal asymptote. But as we do the limit as x approaches positive infinity, that will be positive infinity. All right, so let's review some solving here. So if we have to solve a problem like this, we're trying to solve for x. Remember, we want to isolate the e part. All right, so we're isolating e to the -4x by dividing by the 200. Then we're going to take the natural log of both sides to eliminate the exponential function. All right, so that would mean that we can take that power out in front of the natural log. And so we have -4x ln of e equals ln of 3 over 40. And then we simplify. So the ln of e, remember, those cancel out, and we just get the exponent, which was 1. And then we have natural log. So then to solve, we're just dividing by the 4. And you can keep it like that. That's our exact answer. Okay, the approximate is about 0.648. Okay, make sure to do 3 decimal places at least. Okay, and then if I'm solving something like this, then the first thing we do is exponentiate both sides. Notice that the natural log is already isolated, so we can exponentiate both sides. Exponentiating, remember, means that we're going to raise both sides with a base e. Okay, so each side becomes the power on the e. That's called exponentiating. So then we can simplify using our properties. So if I have e to the ln of x minus 2, then that's just going to be x minus 2 times ln of e. ln of e is just 1. Okay, it's like e and the ln cancel out. Okay. All right, so then all we have to do is solve for x. And then we have that. Just keep it like that. That's totally fine. That would be your decimal answer. Okay. So what we care about is the calculus. And the most intriguing and useful characteristics is that it's its own derivative. So we have some pretty nice, easy, you'll love doing derivatives and integrals of e to the x. Because the derivative of e to the x is simply e to the x, and the derivative of e to the u, so if I have something else besides just x as the power, then we have e to the u times du dx. You're just doing that chain rule. Okay, and here's how we can prove that e to the x is its own derivative. If I start with ln of e to the x equals x, that's that property that we were just talking about with the compositions of the inverse. Let's take the derivative of both sides. All right, so if I take the derivative of ln of e to the x, okay, we're using, think of that as ln of u, right? So that means I'm going to do the derivative of u over u. So the derivative of u we're keeping as the d dx of e to the x, and then the u part is just over e to the x. So that's where I'm getting that. And on the right-hand side, the derivative of x is just 1. And then if I multiply both sides by e to the x, then I get the derivative of e to the x is simply e to the x. All right, so let's do this one. We're going to find the derivative of x squared e to the negative x. All right, so notice that this is a product rule. So if we keep the first one the same, x squared, then we take the derivative of e to the x. So here we have a u, because it's not just e to the x, it's e to the negative x. So you have e to the negative x, so keep it the same, and then multiply by the derivative of your power. So that's just -1. Then you also have the same thing, so e to the negative x, so that stays the same, and then we're taking the derivative of x squared, so 2x. Simplify that out a little bit. So if we factor that out, we'll factor out the e to the negative x, and then they both have x in them. So we have x e to the negative x. That leaves me with a -1 times x in the first term, and then just 2 in the second term. And then you could always put that e to the negative x in the denominator. All right, so again, I'm showing you how AP and the book might rewrite their answers different than that first line. All right, let's do this one. So we're going to find the derivative of this. Let's use our powers of the properties of logarithms to simplify this. Remember, that's very useful. We can separate this into 2 separate natural logs. All right, so we have natural log of 1 plus e to the x minus natural log of 1 minus e to the x. Okay, now we can take the derivative. All right, so remember, I've got my u in the denominator, and then the derivative of u goes in the numerator. So 1 plus e to the x is in the denominator, and the derivative of that is just e to the x. Same thing in the second term, 1 minus e to the x is in the denominator, and then negative e to the x is the derivative of that. And now we can just simplify this. So again, here's the derivative part, and now we're going to simplify it, make it look more like what the back of the book would do or a multiple choice problem would do. So they're going to factor out an e to the x. Notice that in the second term I have a negative in front of the fraction and a negative e to the x. So that's going to become a plus. And then we're also going to get a common denominator. So I'm going to multiply the first term by 1 minus e to the x, and then the second term by 1 plus e to the x. So that's where your numerator is coming from. And then we're going to have that denominator down there. Notice that the ones are both positive, again, because of that negative makes that positive. Then all we have to do is simplify. All right, so I have 2 in the numerator, and then I have a difference of 2 squares pattern. So that's going to be the same as 1 minus e to the x squared. So keep in mind that e to the x squared, if we use those power rules, that's the same as e to the 2x. So that's where I'm getting 1 minus e to the 2x in the denominator, and then 2 times e to the x in the numerator. That e to the x that was factored out front, that came back up into the numerator. Please feel free to pause and try some on your own as you need to. Okay, so then now if e to the x is its own derivative, then think about the integration. How do we do the integration? Well, it's just going to be e to the x plus c. All right, and then if I have e to something else besides just x, I have to make sure that the du is also in my integration, just like normal u substitution. All right, and then if I have that, if I have the du, then it's just going to be e to the u plus c. So let's do an example. All right, so if we look at this, what should we make our u? So think about this choice carefully. All right, if you just make u 2x, like if you're thinking it's e to the 2x, so that would be the u, think about what your derivative would be. It'd just simply be 2. And then you have all that extra stuff down in the denominator. So choosing u as 2 to the x is not going to be very helpful. Instead, we're going to think back to our last homework assignment. And if we have a fraction, it's better to make u the denominator and then see if our du is in the numerator. Okay, so we're going to choose u to be that denominator, 1 plus e to the 2x. Then our du is going to be 2 times e to the 2x, dx. All right, and notice that we have all of that in the numerator except for the 2. So we can multiply by the 2 inside and compensate by dividing by 2 on the outside. All right, or if you want to solve it for what's there, it's just going to be du divided by 2. So either way you look at it, it's going to be 1/2 integral of 1 over u du. Okay, so if I do the antiderivative of that, that's just ln. Okay, so this isn't even using our exponential function rules yet, all right, except for calculating the du. All right, don't forget to replace your u. So we have 1/2 ln of 1 plus e to the 2x plus c. And keep in mind that the book might take away those absolute values. Why? Think about why can I delete the absolute values? What's special about 1 plus e to the 2x? Keep in mind that what we originally talked about, the domain of e to the x is all positive, or I'm sorry, the range is all positive. So those will all be positive answers, right? So e to the 2x, that's just going to be squared even. So all of those will be positive inside that natural log. All right, let's try this one. Here we have a definite integral. And think about, what are you going to make your u? So here, making the exponents your u makes more sense. Because if u is secant of 2x, what's your du? Remember your trig derivatives. Derivative of secant is secant tangent. And since I have secant of 2x, I need to do secant 2x, tangent 2x, and then do the chain rule, right? So I need to multiply by the 2 dx. So we have all of that except for the extra 2. So we're going to have to compensate by doing the 1/2. So I have, seriously, all I have is 1/2 e to the u du. And that's an easy integration, right? And we talked about how instead of plugging back in the x for u, we can change the limits of the integration to be u's. So if I plug in pi over 2 into secant of 2x, then I'm going to get -1. So that's why that top limit of integration is -1 now instead of pi over 2. And then if I plug in pi over 3 into the secant of 2x, then my u is going to equal 2. All right, so that's all we did there, is we just put those limits of integration in there. So now we don't have to worry about plugging x back in for u. So if I do the antiderivative of e to the u du, it's just e to the u. And now we're going to be plugging in -1 and then -2. So I have 1/2 in front, e to the -1 minus e to the -2. So you can simplify if you want and get a common denominator. And you can factor out that numerator. All right, lots of ways to simplify that. All right, and then just keep that as your exact answer. Okay, so simplify those e's. And that's fine. You don't have to get a decimal or anything like that on the AP or on the test. So please work on your homework and help each other out, ask questions, and then I'll be back to answer any more questions that you still have.